Today we are discussing cleaning, rinsing, and drying of the engine air path, which is commonly referred to as a compressor wash. Our maintenance manuals provide detailed instructions for accomplishing these vital tasks, but the finer points are commonly overlooked. After a brief introduction, we will follow the maintenance manual through each step of the process to provide a better understanding of the requirements and task navigation. Why do we call it the air path? In our Arriel engines, 98% of the air pulled through the inlet is used for combustion. We call this primary air. The remaining 2% of the airflow is called secondary air. This is the internal air system, which serves several purposes on all of our engines. It pressurizes labyrinth seals, balances the rotating forces, dilutes and cools the combustion gases, stabilizes the flame in the combustion chamber, cools the nozzle guide vanes, turbine faces, the turbine shaft, and the turbine shroud. So why does the air path require cleaning? A dirty air path reduces the efficiency of the gas generator, which results in lower power margins or incorrect power checks. It also leads to damaged internal components, resulting in a significant increase of expense at repair or overhaul. Parts with life remaining that would be otherwise serviceable must be scrapped due to preventable damage. In the Arriel on the left and Arrius on the right, primary air and secondary air reach the combustion chamber through precisely drilled holes in which particulate matter from the air accumulates, obstructing or completely blocking them. The accumulation of material and reduction in airflow results in several issues. Accumulation on compressor and gas generator turbines leads to corrosion and erosion, which reduces the gas generator efficiency. Lost airflow and compression requires the gas generator to spin faster in order to produce the volume of combustion required to maintain the power turbine speed or torque setting desired by the pilot. Higher N1 requires additional fuel, which produces more heat, or T4.5. Accumulation of atmospheric contamination and salt deposits blocks air passages in the combustion chamber, which disrupts the thermal environment. Cooling and dilution of the gas path, and combustion efficiency, which damages the liner and reduces engine performance. Burning of dilution tubes and unequal airflow between the front and rear swirl plates disrupts the flame position and consistency, causing it to shift closer to the obstructed side, resulting in warping and cracking. The image on the left shows equal airflow through the front and rear swirl plates, keeping the flame centered in the combustion chamber. The image on the right shows blocked airflow on the front swirl plate, allowing the flame to shift, resulting in heat damage, such as warping or cracking, as seen here. Buildup on gas generator turbine blades causes a change in flow. Damage to the airfoil of the HP turbine stages from erosion, corrosion, burns, salt, or laterite deposits, cracks or loss of material on diffusers and stators, and rubbing. The damage to these critical parts results in a decrease of turbine efficiency and reduced engine performance. These Borescope images were sent by customers requesting assistance with determining the type of damage in their engines. We receive these types of pictures and questions often. Most of the time, as was the case with these, what appears to be damage, cracks, or flaking are actually Borescope tracks through the dirt or chunks of accumulated contaminants that have flaked off within a very dirty air path. These engines are perfectly serviceable, but very dirty. Do yourself a favor and clean the air path prior to inspection with the Borescope. The air path cleaning and inspections by Borescope work together as a team. Routine cleaning keeps the buildup of material from creating or covering potential issues, and inspection by Borescope tells you how well your cleaning technique is working. Blocked cooling holes of the nozzle guide vane, or NGV, results in thermal damage and cracking. Damage to the power turbine, such as impacts and distortion, erosion, corrosion, and cracks on the stators, affects the efficiency of these expansion stages. The most significant issue in this area is rubbing, which causes a reduction on the turbine's expansion ratio and efficiency, which significantly lowers engine performance, generally by affecting the power without reducing the temperature margin. Aircraft equipped with barrier filters are not exempt from air path cleanings for several reasons. The filter installation does not stop all of the particles in the environment from reaching the internal passages of the engine. Oil pulled from the filter helps atmospheric particles adhere within the engine. This is another reason to thoroughly clean, dry, and oil your inlet filter properly. Too much or too little oil are equally detrimental. Compression stages prior to the combustion chamber are generally cleaner with no erosion, but byproducts of the combustion process are corrosive and accumulations must be chemically cleaned to prevent damage to the high-pressure turbine blades. The high-pressure turbine blades pictured here are from a barrier-filtered Arriel 2. Untreated combustion byproducts have corroded and eroded the tips of the blades. How do we prevent all of this? Through routine cleaning of the air path, we maintain power margins and prevent costly damage. Guidance for cleaning, washing, and protection is contained in Chapter 71 of the Maintenance Manual, Power Plant, Section 71-01. Beginning with the General Information section, we will dive into the details of the procedure to provide a better understanding and allow you to get the most benefit from your efforts. The task numbers, titles, and wording vary slightly between engines, but the information contained in each is the same. Please remember, as detailed as this review may be, references and task information change often, so you must consult the current revision of the applicable maintenance manual prior to performing any maintenance procedure. Let's get started. The Rinsing, Cleaning, Protection General subject explains the effects of operation in the various environments, defines those environments, and provides recommended procedures to prevent engine deterioration. Operation of a turboshaft engine in dirty air will have an effect on its efficiency and cause damage. In order for it to continue operating satisfactorily, periodic treatment is required. Salt-laden air will result in corrosion, which causes weakening of the materials, along with the formation of deposits, all of which decreases engine performance. An engine is used in a salty environment if the aircraft is operated from a boat or operated near salt water, within 3 miles of the shore or 1,000 feet above the surface. If your engine looks like any of these, it has been exposed to a saline environment. Contamination from insects or industrial pollutants leads to the accumulation of deposits and corrosion with the resulting loss of performance. An engine is used in a polluted environment if the aircraft operates around industrial dust from an industrial town or environment. It operates in natural dust if the aircraft takes off or lands on unpaved areas, flies over volcanoes or quarries, or when insects can be ingested. This is a broad definition that could be applied to the vast majority of helicopter operators, since this is exactly what we do. General Service Letter 2332/05 provides guidance for engines operated in polluted or volcanic atmospheres to include factory smokestacks, fires, cooling towers, or other contaminants. Operation in a sandy atmosphere results primarily in deposits in the hot portions of the engine, which leads to a loss of performance. An engine is used in a sandy environment if it takes off, lands, or hovers in ground effect over unprepared areas within sandy regions, or if it operates over deserts or similar environments at any height with a high concentration of airborne or rising sand particles. We provide several recommendations to prevent engine deterioration based upon your environment. Rinsing during cranking or with the engine running. The rinsing task is defined as a fast cleaning procedure which removes some of the corrosive or salty materials and mineral deposits from the air path after the engine operates in a corrosive, salty, or sandy atmosphere. You will see a caution later in the rinsing task stating that the running rinse can be applied in certain circumstances, but rinsing during ventilation or cranking is the recommended method. Throughout this process, you will also see the terms cranking or ventilation. They are used interchangeably, referring to the engine motoring. The chemical cleaning task is performed during cranking only, utilizing a degreasing product to remove accumulations of dirt, insects, unwanted oil, etc. The internal and external protection tasks treat engine internal and external surfaces with a corrosion inhibitor and water repellent product. General Service Letter 3055/20 supplements the maintenance manual guidance along with the chart to aid in determining the environments and their effects. Once the operating environment has been decided, the frequency of engine cleaning task provides recommended frequencies in which to treat the engine. The table of recommended frequencies provides intervals for rinsing, chemical cleaning, and external protection, ranging from a daily rinse in a corrosive, salt-laden, or sandy atmosphere to a 100 flight hour periodicity outside of a particular atmosphere, as defined in the previous task. As stated twice in the task, in the case of combined atmospheres, our recommendations are cumulative and based upon the most restrictive frequency. These recommendations can be adjusted according to operational constraints or the installation of various inlet barrier and vortex filters. Contact your field rep to find a schedule that is best adapted to your environment and operation. Now that the environment and frequencies have been determined, we need to choose an approved cleaning product. The engine cleaning product's general task contains information and links to the approved and recommended cleaning products, their mixture ratios, internal and external protection products, and water quality. A few important details to note within this task are: the cleaning mixture ratio will be adapted to your environment and ambient temperature. The rinsing and cleaning operations are more efficient if the mixture is heated to a maximum of 140 degrees Fahrenheit, which can be done by using hot water prior to mixing or by heating the blended mixture with an immersion heater. For those performing this procedure in an environment below freezing, an anti-icer is not mandatory if the mixture is heated and the drying run is performed immediately afterward. Scrolling through the task, you will find the mixture for rinsing table, followed by the ratios. The first table shows rinsing mixtures with a lower concentration of cleaning product. These are adapted for the operators in saline and sandy environments who perform daily rinses. Following a routine chemical cleaning, the rinse is performed during ventilation or cranking without a cleaning product. The next table contains the mixture ratios of the cleaning product and anti-icer for chemical cleaning. This is the information we will use for the routine chemical cleaning of the air path. The notes that follow address mixture ratios for specific products, followed by the approved RTU or ready-to-use products, which do not require dilution with water, but any necessary anti-icer should be mixed in accordance with the ratio in the table. Using the mixture ratio chart, with room temperature water and the ambient temperature in our hangar above 41 degrees Fahrenheit, we will not require anti-icing additive, so the mixture ratio is 20% cleaner with 80% water today. The next table links us to the internal and external protection products. And finally, we see the water quality section. Water quality is a very important part of the rinsing, washing, and cleaning operations. Use of non-conforming water can cause a buildup of deposits and further contaminate the engine rather than clean it by creating air path fouling and corrosion due to the quantity of chloride, sulfate, and alkaline ions in the liquid. All of these lead to a reduced performance and a significant increase in repair costs. You must use distilled or demineralized water meeting the specified standards. If neither are available, water meeting the minimum specified quality can be used, but only during the cranking procedure. Moving back to the cleaning products task, the link in the table takes us to the list of recommended fuel, lubricants, and special products located elsewhere in Chapter 71. Work your way past the fuels, additives, and lubricants until you reach special products. Observe the caution or warning which states that approval from Safran Helicopter Engines is required to use products not specified on the list. We see the cleaning products used during engine cranking or ventilation, the cleaning products used on a running engine, internal or external protection products, and the approved or recommended anti-icing products. Today we are using ZOC 27 for the routine chemical cleaning. Now that we have determined our environment, the cleaning frequency, the cleaning products, water quality, and their mix ratio, we can get to work. We will be performing the cleaning and rinsing tasks on an Arriel 2B1 and a pair of Arrius 2B2s, beginning with a chemical cleaning procedure. Note, caution, and warning boxes throughout our maintenance manual contain information vital to the task. Please take the time to read them during this task as you would in any other procedure. Below the general warning regarding the dangers of anti-icer and cleaning product vapors, we see two cautions. The engine T4 must be below 70 degrees Celsius before beginning this task, and if you are performing this task shortly after engine shutdown, this process is not to be accelerated by ventilating or cranking the engine. Allow the engine to cool naturally if this task is performed shortly after engine shutdown. The first step in cleaning or rinsing an Arriel 1 or 2 is to configure the engine by closing the bleed valve. An open bleed valve prevents the cleaning and rinsing mixtures from reaching the intended areas within the air path by spilling out on top of the engine or through the overboard duct. Bleed valve closure can be accomplished in a couple of ways. It can be covered with a locally manufactured blank, which requires removal of the screen or duct, or by using the Safran bleed valve blanking tool listed in the task. We can apply 101 psi of shop air to the bleed valve air inlet, which holds it closed. The next caution in the Arriel 1 task pertains to the P2 pipe between the fuel control unit and the P2 air tapping on the intermediate casing. Removal of this pipe was recommended for a period of time in response to water ingestion into the FCU acceleration control chamber. Frequent removal and installation with over-tightening of the fittings was causing damage by work hardening of the pipe. A loss of P2 supply at the FCU will cause the engine to roll back from flight idle. We have since proven that when the tasks are performed in accordance with the quantities and flow rates specified in the procedures, it will not lead to FCU water ingestion. So removal of this or any other pipe is not necessary. For all Arrius 2B1 and pre-TU 165 Arrius 2B2, the cleaning and rinsing tasks instruct you to disconnect the main fuel injection line between the adjusted valve and the drain collector union. This is necessary because the pressure level reached during the air path cleaning under engine cranking can cause the drain valve of the main fuel injectors to open. With the drain valve open, cleaning liquid which has accumulated in the combustion chamber can move up through the main fuel injectors, through the injector drain pipe, and back to the drain collector, which returns to the fuel tank. Not a good situation. Disconnecting the drain line and capping the collector prevents any cleaning or rinsing liquid from reaching the fuel tank. For Arrius 2B2 powered aircraft, we released TU 165 in late 2022, which, in conjunction with Airbus SB EC 135-71-055 or EC 135H-71-003, modifies the routing of the drain. Once your aircraft is equipped with the new configuration, the line will no longer need to be disconnected during this procedure. Next, we will prepare 4 liters of the chemical cleaning mixture. As determined from the table, the 4-liter mixture consists of 20% cleaner and 80% water, so 800 milliliters of ZOC 27 and 3,200 milliliters of distilled water. In accordance with the note that follows, we will homogenize or blend the mixture prior to using it. For aircraft with a manual heat control, we will ensure this and any other airframe air tappings are closed. The step now instructs us to adjust the pressure generator to achieve an injection flow between 7 and 8 liters per minute, which is right at 2 gallons per minute. The note that follows this step allows for use of a pressure generator other than the specified Safran tool, as long as it can be connected to the spraying device and provide the specified flow rate and volume during injection. Operators of our engines have many different delivery methods for injecting the cleaning and rinsing liquids, from a simple portable spray tank with a handheld wand directed at the inlet, to a heated, electric pump-equipped 2-tank wash kit connected to the airframe fitting. However, more often than not, these methods are used without regard to the prescribed quantities or flow rates specified in the maintenance manual, which has several potential risks. Delivery of a liquid at a rate higher than specified can cause damage to the engine. A slightly lower rate is not harmful, but keep in mind that additional ventilations will be required in order to admit the specified volumes. A lower concentration, volume, or abbreviated soak time will not adequately remove contamination. And the cleaning chemical is a commercial degreaser. An excessive concentration or volume of the chemical, excessive soaking time, improper rinsing, and skipped or insufficient drying ground run will lead to internal staining, pitting, and corrosion as pictured here. 4 liters of cleaning mixture injected at the maximum rate of 8 liters per minute requires 30 seconds of injection time. Have you ever verified the flow rate of your equipment? For those with large washing and rinsing tanks, how do you verify the quantity that was delivered? With the known delivery rate, we can verify the injection quantity. Add water to your tank, grab a stopwatch, and spray the water into a bucket for 30 seconds. How much did you collect? If the bucket has much more than 1 gallon, your flow rate is too high. On site today, we have a pair of rechargeable fire extinguisher tanks, which many of you have used. We filled the tank, we charged it to 100 psi, purged the line, and charged it back up to 100 psi. We collected 4 liters in 1 minute. This is much less than the 7 to 8 liters per minute maximum in the maintenance manual. So note that it will take 4 15-second ventilations to inject all 4 liters of mixture. Consider the following when configuring your washing equipment. Set the equipment up correctly to make this task easy to perform. Protect yourself from FOD with an inline filter on your locally manufactured spray system. A flow limiter is the most reliable and predictable method for flow control. Be aware of contamination sources with a multi-tank system. Complacency can lead to engine removal for repair. The 2 cautions that follow advise you to follow the starter limitations listed in the flight manual. You will find these values in Section 2, Limitations, or Section 4, Normal Procedures of the Rotorcraft Flight Manual. The maximum cranking or ventilation times are typically 15 to 20 seconds and can vary depending on the rating of the starter generator and battery installed, or with the use of a ground power unit. Always use a ground power unit. These repeated ventilations are hard on an aircraft battery, which can set you up for starting trouble later. Take the time to familiarize yourself with the configuration and related limitations of each aircraft you are maintaining in order to prevent damage to the battery and the starter generator. One last item to note prior to the injection procedure is our recommendation to activate the airframe boost pump or prime pump anytime the engine is cranked or ventilated. Activation of the electric fuel pump ensures fuel is present at the HMU or FCU, providing better cooling and lubrication of the fuel pump components, ensuring their long-term reliability. Arriel 2 Service Letter 2970, released in June of 2016, provides more detail. Let's absorb what the manual has given us. Again, the wording varies by engine, but the message is consistent. The Arriel 2 manual states, inject the chemical cleaning mixture during some crankings, followed by, let the chemical mixture soak in the air path for 5 to 20 minutes between each cranking, but do not let it dry in the air path. The notes directly below the step add, the accumulated time the chemical cleaning mixture soaks in the air path is an important parameter for chemical cleaning efficiency. Inject all of the cleaner in as many injections as it takes. Let the cleaner soak for a minimum of 5 and a maximum of 20 minutes between each injection. Maximum soak equals maximum benefit. Allow the cleaner plenty of time to dissolve the contaminants, but do not let it dry. Recommended products such as ZOC MX and B&B 3100 are very aggressive and do not contain corrosion inhibitors as some of the other products do. Soaking beyond the maximum time, allowing the cleaning mixture to dry, improper rinsing or drying can cause corrosion within your engine. The final 2 notes tell us: begin injection once the engine reaches 10% N1 and stop injecting at 10% N1 during the rundown. Putting everything together, we can create a checklist. 800 milliliters of ZOC 27 with 3,200 milliliters of distilled water provides the 4 liters of cleaning mixture. Keep in mind, the maximum injection rate of 8 liters per minute will require a minimum of 30 seconds of injection time, and very few specifically configured aircraft will allow a starter run for that length of time. So this procedure is going to require more than 1 injection. In our case, we are looking at 4. We will follow each injection with the recommended soak time. We'll begin the first injection on the Arriel 2. While we wait for the Arriel 2 to soak, we will do the same on the Arrius 2. After the last injection of cleaning mixture, we are instructed to rinse the air path by cranking. We can get set up for that while we wait for the last shot of chemical mixture to soak. The rinsing task is very similar to the chemical cleaning task, with a few minor differences depending on engine type. The note or caution at the beginning of the task tells us Safran Helicopter Engines recommends the more efficient rinsing during ventilation, but operational constraints can substantiate a running rinse procedure. This is in reference to the running rinse as a standalone task for those conducting daily rinses. This is not applicable to the rinsing following chemical cleaning. The running rinse can remove particles from the colder sections of the engine, but will be vapor by the time it reaches the combustion chamber or gas generator turbine. The rinsing task begins with the instructions for the rinse of a running engine. For those operators using this specialized procedure, make note of the following. With the engine at ground idle, 6 liters of rinsing mixture is injected at 2 to 3 liters per minute on the Arriel, and the Arrius specifies 0.8 to 1.5 liters per minute, which is much less than the rate of 7 to 8 liters per minute used during ventilation. This will require as little as 2 minutes of injection time on the Arriel, up to 7.5 minutes on the Arrius. Cold water injected into a running engine at an excessive rate will cause damage to the engine. Do not allow the N1 to decrease by more than 10% during injection. The engine must remain running for a minimum of 5 minutes following the water injections. Longer is fine, but do not shorten the drying run. And of course, verify that the water meets the minimum quality standard. The chemical cleaning task sent us to rinsing during cranking or ventilation, which is found in section C of this task. The engine is still cool and configured following the cleaning procedure. Ambient conditions dictate that anti-icer is not required today, so our mixture is 100% distilled water. If additives are used, ensure the combination is blended prior to injection. The rinsing injection rate remains the same, 7 to 8 liters per minute as a cleaning. With an additional 2 liters of rinsing water for the Arriel, it will require at least 1 more set of injections at the maximum rate to move the requisite volume of water through the engine. And with our rate today, we need 2 more injections than the cleaning required. Again, during the ventilation, we begin the injection above 10% N1 and stop injection at 10% N1 on the rundown. Note that the rinse does not require a soak time between injections, as is the case with the cleaning procedure. Inject all of the rinsing mixture in intervals while adhering to the starter limitations. After the final rinsing injection, you can restore the engine configuration. The final step in the process is the drying run. This is equally as important as every other step in the task and should not be skipped or shortened. Start the engines, stabilize them at ground idle, and keep them in operation for a minimum of 5 minutes for an Arriel and 10 minutes for an Arrius. The ground run following the rinse is more than removing any water left at the bottom of the combustion chamber. Running the engine removes standing water from the bearings and recesses and brings the oil up to operating temperature, which removes the remaining moisture from the oil system. Air path cleaning applies to every engine operated in any environment, and while every detail in this task is important, the key points are aircraft configuration, bleed valve closed, main injection drain line disconnected, water quality, precise cleaning chemical quantity and mixture ratio, do not guess, injection flow rate, verify your flow rate, soak time, rinsing quantity, and the drying run. Take the information presented and apply it going forward. As always, contact your Safran Helicopter Engines field rep with any questions or for customized procedures.